Good afternoon, everyone. Thank you so much for the invitation and the introduction. As you guessed, I'm not British, so I thought I would start by a little video just for you to get used to my strange accent. A brick doesn't know his neighbor, it's just a brick. Can one know the next one, and get a chain? About 10 years ago, I thought, what if we actually look at the principle of monocoque, the principle of boat, which is trying to transfer the force always along the surface and never go perpendicular to it. To describe something like that, we probably want to connect using what I would call tangential continuity. Linear parts describing a non-linear type of geometry. It's more than a question for me, it's literally a fascination. The difference between intensive versus extensive curvature. What I would call extensive curvature is what has been presented before through the work of Ryotto. That the bubble model is more performant than the box. He certainly proved it to us. But if you take a bubble and you scale it up to the scale of a room, up to the scale of a building, what looks like being double curved is actually planar at every single smaller description. So intensive curvature is still trying to optimize double curvatures, but we fix a maximum radius, which means that instead of having one single surface spanning from one side of that room to the other, you have to go through tubular elements, you have to go through split, recombination, resplit, merging together, resplitting together, etc. It's thinner than your credit card, less than 1 millimeter thick aluminium, and yet you can stand on the top of a structure like that. It has depth, it has porosity. It's a limit, but it's not a limit. You start to wonder, is there an order? If there is an order, what exactly is that order? But also some people start to project their own background. You come from the sea, some people will read coral, some people will read flowers. It doesn't matter. But it matters that they engage, that they start to wonder about the structure. That's what's important for me in terms of architecture. Perfect. As you guessed, I'm probably going to talk a little bit about computation and digital fabrication. I think the title today, I try to call it structural segmentation and dealing with ultra-thin surfaces. Just to bring you back a little bit, end of 90s, early 2000, anything who looked like complex in architecture had to be decomposed as sum of elements. Sum of planar elements, or you go the complete opposite road, the molding roads. The planar guys had no choice than actually decompose what looked like a complex form into a sum of triangles. That was end of 90s, early 2000. 2004-ish was the race of who could decompose the first one as a sum of quads. Of course, triangle, cutting them into some of the material are pretty expensive and deal with all sorts of problem of nodes. The quads came, and then the polygon came. That's actually one of the very first surface just described as a sum of polygons. You take any kind of geometry, mesh surface, you can relax it, you can describe it as a set of panels, unroll them, nest them, digitally cut them, and eventually whatever is going to be your final form, you can reconstruct it. Those went through all sorts of series of installation at the time. We're talking about 2005, 2010. There was plenty of those. The problem is, an installation like that, barely 2,000 parts, took about 4%, 10 days, full-time, plus all series of helper on the side. We knew directly the premise was probably wrong. The premise at the time was the very many. Can we describe complexities through the very many, each being unique, each being responsive to all sorts of criteria, structure, environment, name them, you can describe it. But we didn't know how to recompose that thing. And the name of the studio was misnamed. It's called Theverymany. And actually, what we discovered from that is the next 10 years of the work had to address the opposite. How do you go from the very many to the very least? How can you reassemble as fast as possible those type of structures so you can eventually reach the scale of architecture? So you take a geometry like that, just a random one, non-linear, a series of branch, a mesh. Why is that non-linear? So that you can't just array panel onto that? The difference is, it was that the first discovery, the first little invention we made was the idea of, if we can't assemble 2,000 panels because it takes too long, what if we reduce the number? What if we start to recombine those panels into, let's say, a series of linear stripes, for example? So you take that same geometry, you can start to describe it as those elements, and now you might only have 400 or 500 of those. You can reassemble it not only faster, but also you're away from the paradigm of the singular. You're away from the paradigm of a panel, a name, a neighbor. Here you suddenly have one panel, many, many neighbors, which means you have redundancy as well in terms of structure. Very quickly we arrived into a lack of knowledge of geometry. We are architect by training. We do love to write computation, we do love to write codes, but we are very limited into actually our pure geometry knowledge. What we can do, though, is program and program many. Many can often solve on the computational side, not on the material side, can solve many, many problems. So we went from early class of descriptive geometry to what we would call search protocol. So you take a geometry like that, an installation for the Centre Pompidou in Paris, and you can see how it's generated, a series of points, from points network, from network to tubes. Then we arrive to a geometry which we call nonlinear. How do you describe something like that? You suddenly have to have a series of little agents running in parallel, because the previous methodology, which was just recombination, none of the panels would know each other. If they don't know each other, sooner or later, they will trigger a mistake somewhere or a non-optimal solution. Here they can run in parallel, they can have all sorts of different behavior, which is where the color came. And the reason why it's black and white was actually suggested by the Centre Pompidou just to express the nevros of those behavior. We call them schizophrenic. They're actually fighting each other. You never want to find the best rule. You never want to find the best case. Because if ever you find the best case somewhere, you will trigger a mistake somewhere else. You will trigger a problem somewhere else into the geometry, because we are into those nonlinear type of geometry. From there on, we discover another advantage of those geometry, just going empirical from there, is the difference between intensive and extensive. Basically, extensive is what every Frey-Otto protégé is trying to do, is the use of double curvature structure through geometry. Unfortunately, most of the time is just a flat mesh that one way or another you inflate, one way or another you relax. But the mesh can exist flat. Intensive is slightly different. He is actually trying to use double curvature, but actually trying to constrain the radius that you're allowed to use. Therefore, you start to have geometries that become tubular. Those tubular start to branch, recombine, open up, rebranch, rejoin. And you eventually arrive to a geometry in those environments like that. I'm an architect. We don't always only evaluate things in terms of efficiencies. So when we arrive to there, that's the moment where we're away from the digital and we can finally evaluate the type of installation, the type of space created. By doing so, we can create new problems that can eventually make the digital progress. You can see some of the inside. But the advantage of those type of system is what I would call self-formed frozen tension. We are not anymore in tension. Those geometry are using a lot of relaxation processes, a lot of springs type to arrive to that fact, but we do not have any primary structure. Remember the presentation a little bit earlier this afternoon where it was fabric? They needed that very heavy framework to sustain the fabric. Here you do not need any kind of scaffold, you do not need any kind of mold. It's actually slightly, progressively taking its shape just by connecting one of the stripes to its neighbor. One of them next to the other one, next to the other one module next to the other one, next to the other one, and eventually you get something like that, which is, again, it's less than a millimeter thick, and you can walk 6 meters high onto a structure like that. At the time, we were at the very least impressed ourselves for that. But also, we were interested by the architectural qualities of those environments. It's not a limit anymore, yet it's a barrier to one extent. It has depth, it has all sorts of nonlinear quality. It's not just a partition, it's not just an array anymore. So we brought the question of how do we grow? How do we keep growing in scale? And that idea of walking assembly is key to those systems. Every time we try to actually pre-assemble, pre-module, we start to create elements which are stiff, lack of tolerance. Whereas if you want to grow and actually deal with contractor, which that project was the very first one, which we did not do into the DIY type of model, you suddenly have to find a recipe that's very simple that they can build up onto. So here you can see what I showed before at the video. And a very simple, similar type of geometry, except that we decompose the nonlinearity of the network into a linear set of rings. The idea was, when we did the prototype with that company, they were not able to assemble the prototype. And yet it was the same exact geometry. The reason was they were not trying to go little by little, one ring after another, one rivet after another. And that's the idea of walking. If you walk along, you start building up the geometry, you start building up the structure. Here again, no tricks. It's less than a millimeter thick. You can see somebody walking 15 meters high onto the structure. But nevertheless, the idea is always the same for us. We want to grow scale, we want to grow complexity and reach back architecture. So that idea that the piece, or it's one of its quality of the piece, would be through the intricacy of the part as its limitation. We can't extend endlessly those number of parts. So we went from trying project where we go from intricacy through the parts to intricacy within the parts. A small project, an installation in New York for storefront art and architecture, where here the idea was, what if we do different set of agent? One set of agent has one criteria, fabrication-wise. It has a maximum length, it has a maximum width, it can nest, it has also a behavior so that it doesn't curl too much. And another set of criteria which is trying to follow directly the stress flow, the structural stress flow. So what you can see here, in black it's the material, in white is the void, and you can see the black is driven by exactly where the stress flow goes through. But if you're a structural engineer in the room, you would call me out. It's a total bluff. It's a total bluff because you would not get those type of points, for example, those inflection points. Those inflection points came from those transducer. Transducer is simply a sound device that transforms sound waves into vibration onto the material. That project was a collaboration with a sound artist, so we actually included those points into the analysis itself. But that's where we arrive. We arrive into a geometry where how do you describe something to your structural engineer? It's not just a surface, it's not like a beam or a column. It's not a skin versus a primary structure. If you look carefully, the column, if that would be a column, is actually made from the skin, and the skin itself is structural. But also what is inside at some point becomes the inside of the structure, or the inside of the structure becomes the outside of the installation. There is all sorts of mind games going to trying to understand those type of environment. But also, how do you describe something like that to somebody which is blind? you have to borrow suddenly to all sorts of vocabulary which we are not used anymore into the field of architecture. And I think that's where suddenly a material system, the type of environment you can create, form one, which is a unified system. You can see some of the moments. And a slightly larger one, similar type, in China, this one, where here the behavior was slightly different. One is following one direction of stress flow, and the other one is following the other one. So the porosity is following one, and the parts themselves are following another one. You can see some of the interiors, the kids climbing onto it. And again, that is at the thickest 1.5 millimeter at the thickest. It goes from a little bit half a millimeter to 1.5 millimeter thick. You can see the skin following the stress flow. You can see the two different types of direction, one for the cross member into the parts and one for the parts themselves onto the skin, and expressed at night as a void, where obviously you see the opposite. Anyway, fun stuff, but temporary installation for most of them, except the hanging one. How do we keep growing? How do we become actually permanent, outdoor? How do we sustain to much more than just dead load? Most of the installations are successful if they hold their dead load, but would dramatically fail as soon as a little bit of wind will blow. So we had a simple problem. We knew that we had to keep the material as thin as possible so we can still work it out. We can either bend it or fold it. So what we came up with is what we would call a structural shingle. The idea is pretty simple. It is still a system of stripes, if you look carefully, except that every stripe is overlapping as much as it can with the next one. So the stripe itself stays thin, but the sum of the stripe doubles the thickness of the material. Therefore, you can resist not just to wind, the geometry itself would have taken care of the wind, but you can also start to resist to vandalism. You can start to resist to point load, all sorts of things that shell structure hate. Here you can start to see the tectonic aspect, the shadows on the ground as well, revealing all the tectonic, and a bit of inside. And a different one in El Paso, Texas, a project where we did an entrance for a swimming pool, similar type of ID. This one is 3 millimeter thick. It's a permanent project outdoor using the structural shingles. As you can start to see, inside you see the stripe motif versus outside you read actually a typical shingle type. Inside, the stripes, the running bonds between the parts versus outside the overlap in order to better resist to impact. You can see the dynamic type of shadow onto the walls. Some of the coloration as well. Every part can be painted, of course, into one single color, so the sum of the parts create all sorts of gradients, dark points, highlights, and the roof. But still, we did end up into another problem. Now suddenly our shingles, in order to get produced, the parts themselves have to be actually bent, have to be folded. More processing on the parts equals the time you save on site, you lose it in the shop. So we thought, what if? We have all heard about bending active, of course. That idea of being able to produce a structure, for example, flat like Frioto, and push it up and lock it into place and then release all the scaffold and all the edges condition. But here it's slightly different. It's an idea of trying to be a bending active assembly, where a project like that for Astana, Kazakhstan, for the World Expo, it's a permanent piece. It's 14 and something meter high. The total thickness of the piece at its very maximum is 6 millimeter thick, and yet it's a permanent piece. You can also see how it goes from double curvature, intensive curvature, we'll see inside, which is those pipes elements, and at the bottom, to resist to the dead load, the pleats So how do you go from a continuous, single continuous surface up to a pleated surface at the bottom? All those moves has always multiple reasons. They have experiential reasons, but they also have structural. Why do we have those closed elements? Just to be able to keep that intensive curvature we were talking about before. If we wouldn't have those, we'd just be into extensive, which is not enough to sustain with load. Of course, those type of structures are driven through wind condition. You can see all sorts of moments. Here it's a 3-layer system, not folded for most of it. 2 layers going in the best direction for structure, 1 layer acting as a connector and increasing the material thickness for impact. Here you can see the transition between continuity to actually pleated continuity. Some of the intensive curvature I mentioned before. And at 9 for that. But still, what we run into in that type of system is obviously high number of parts. The parts themselves very easy to produce. We got rid of the bending. We got rid, sorry, not of the bending. We got rid of the folding part, the folding aspect. The problem is actually forcing them one by one, growing, walking assembly is extremely hard when you have 3 layers. So that's the last one we just finished this year, where we call it compound curvature for now, because it's that idea of taking a little bit from every system we've done in the past. It's a multi-layer in order to resist to impact. It's a small project permanent in North Carolina, Charlotte, where we also mixed positive curvature, negative curvature. We also blend into different systems. It has a cross lamina in diagonal at the bottom. Those ones are labyrinthic. So it's trying to go along the surface, become more and more free from one and unique system of descriptive. It goes from purely continuous. Some of those parts are folded, some are not folded. There is actually 3 different types of thickness of aluminum, up to literally creased also here. Some of the inside. It's a little playground for kids. You can see some of the labyrinthic parts versus here you can see all the very diagonalized version into different direction because of the download, heavy download. And of course a bit of playfulness. Photo by Narrow, by the way, which is somewhere in the room, I really advise. And some of the inside detail. Anyway, sometimes again, I mean, I'm trying to say before, respond a little bit to that quote before. What is the question? And I think in the work we're trying to do, we try to stay very focused on that question. That question is, how can we grow those very ultra thin surface? How can we grow them both in terms of scale, but also grow them by adapting to different type of system? Sometimes we cannot afford curvature, or not the way we would like it to be in terms of intensive. So here is a bit of an earlier project where in those cases we would just, that's a more Frioto-esque type of process where the mesh can exist flat. Most of the projects which are non-linear, you cannot take the geometry, flatten it down, you would have all sorts of self-intersections. For example, a simple inflation has 2 processes, inflation of the mesh, pleats of the mesh. But here is what I wanted to show on that project, is part of that progressive assembly. Not only it's progressive assembly, but you can also see here a charming lady which is assembling the piece itself. As you can see, there is only 1 scaffold here. There is absolutely no temporary mass to support anything. There is no mold present. She just has 1 rule. Every part she needs to be able to carry the part on her own. She arrives, she used the piece itself in some way of self-scaffold, if you will. You can see her here. The only reason why we have the scaffold is in order for a person to come, climb it, feed her the part, and she would connect it. The reason also why it's different than a traditional vault, a vault would not sustain before you have the keystone. Here you do sustain is because each of our structure, despite being ultra thin as per any other system, is actually always oversized. Oversized because wind drives, it's never the load drive. So the load of a person climbing is nothing for a structure like that. This one is computed for 60 psf of wind. It's 3 millimeter thin as well. Here you can also see the difference in terms of architecture for us, what is the signal which is trying to trigger curiosity versus the experience. The experience is something to provide an experience, something else to get people to come back. The idea is obviously to have always at a moment something else to discover, either a coloration somewhere you did not notice or the porosity. Here too, for example, if you read the shadow at the ground, the shadow are actually driven by the structural analysis one-to-one. Nobody knows, and it doesn't matter, is what we would call a urban legend. Only the nerdy would actually notice that, if ever they notice that, for that, but most of the people will invent their own story about what the shadow means and would be very proud to share it with other people. And the point loads. Point loads is part of the two projects I want to show to finish on. Point load is what kills any shell. Any shell is extremely hard to resist to. If you focus all your force on any station, if you focus all your load onto a shell structure, the membrane will perforate. Unless you significantly overdimension your shell. So that's really a major problem. And we won a small competition for an amphitheater in a park. Very proud of winning that one. Was also a youngster architect at the time. And we won it for one simple reason, is the person who came to us said, you know, the problem is if I go and see an architect, he's going to try to force that to be a building. And he didn't know we were architects as well for that. But we won it because he told us one thing. 95% of the time, that amphitheater will be empty, will be not programmed. So we thought, you know, that's his program, the main stage. But what if we try to actually make it as open, as multi-use as possible? So all those arches were not part of the program. We thought, what if every arches has a different type of function? We have the stage B, kids just during a walk on a Sunday or a small classroom. We have an accessibility one, we have a dock one, we have the grand staircase, etc., balconies, etc., etc. Some of the structure. But then we went for the geometry, and we started to actually plead the geometry, started to actually be assigned an engineer, not of our choice. Somebody this morning was wishing to get the large firm, Europe, etc. In that case, we actually decided to even hire our own engineer to try to prove that the shell could hold, but it could hold definitely. But suddenly we ended up with that, and that's a structure calculated by Europe. The reason is simple, is point loads. We have 70 points, each following those lines in a very straight line manner because it has to be a grid. Each of those loads is 2,000 pounds, so 1 ton, and Arab took the 70 as one go. So this one can sustain potentially 70 tons of loads. So we ended up having a massive, massive primary structure on that one. So anyway, still an experience, still a project we like, but it brought us to a different client who came a little bit after the amphitheater. And interestingly enough, he had a strange problem. It's become very, very trendy in the US, is every city now wants to break the typical typology of architect, which is the parking plinth versus the high-rise on the top. So you're not allowed anymore in many of them to actually neither show the cars nor show the lights of the parking. So most of them, as the architect, to do, of course, to clad the typology before changing the typology. some of them start to ask different type of creative in order to address some sort of marketing elements permanent onto the facade. But very quickly we arrived into an idea. We wanted something pretty dynamic onto it, but we wanted to address one major issue we ran into when we started to talk to everybody about that facade, is the reflex I wanted to panelize that facade. And by panel, I don't mean the single pixel. I mean one way or another find some sort of grid, some sort of rational grid. And we wanted to go as far away from that because we wanted to be continuous and dynamic. So we finally came up with a motif which has a self-similarity of description. From far you can read, I'll let you read whatever you want to read into it. And little by little you can zoom, and there is a labyrinth within a labyrinth within a labyrinth following some sort of flow up to maybe a part like that, for example. That's one of the parts composing the piece. And started to approach a fabricator for the fabrication, but also an assembler. We managed to convince the fabricator, but the assembler again was resisting, was like, no, let's try to create panel. Let's try to use your system, a two-layer system, pleated to get the structural depth. Let's try to make them in panel. We came, did a mock-up, and they very quickly realized that there is no way on earth they would be able to come with panel of that size and anchor it directly to the concrete of the parking. So we went back to what we actually thought, and that's the beauty of having grown through those installations. A project like that is design build. So you're suddenly not into a ménage à trois. The fabricator, the assembler is working for you, not for the client. So here is a simple sequence of assembly, simply walking onto the facade, the two layers. And basically, you can take a facade like that, which is just hang on a series of points. You can flip it 90 degrees, and you would sustain on a series of stiletto, for example. Here you can see some of the assembly. Very simple. And just to give an idea of scale, obviously some sort of porosity, everything what a cladding has to provide. The pleat, so there is absolutely no primary structure other than the concrete, of course, no secondary system, and that's why we won the competition. We did not want it because of our scheme. We won it because they had planned more than $1 million just for the vertical fins to be able to anchor their facade on the top of it. And we were able to eliminate that, take it into our budget, and with that budget, be able to afford the motif itself continuity. So there is absolutely no breakage of the motif as per a traditional facade. You can see it from far. How we plays with the sun, sometime an highlight on one side, sometime on the other side. The corner condition, and some of the detail inside. But the last one, that's a very tiny one. I think I went very fast through it because I've been told I should expect 5 minutes left. All right. Perfect. It's just the last one, is what I would call freed form. After having been doing that for now more than 15 years of building up, from that first proof of concept of a computational protocol that became little by little in installation, little by little permanent, little by little outdoor, we were so fascinated about the ability of producing at first. Then we were actually very fascinated by the ability to be structural because we needed to sustain. Now we start to compare what I would call freed forms, and there is a slight difference for us about free forms and freed forms. Something like that, which we just completed a month ago or 2 months ago. It's a small, tiny project, permanent in Texas, but it's that mix we are looking for now. A project like that still does not have a primary structure, still does not have a secondary structure. The skin is everything. It's your structure, your experience, your envelope. It's everything. But it's not anymore the kind of limitation we've been programmed, such as Frioto and all that type of Candela type of work. Yes, it's a premise, but right now, you can do much better than that. You can be far more efficient. There is a new technology, just looking into the digital part first. We're still assembling that by hand. It's not anymore a DIY. It goes through every project, goes through a contractor, everything like that. So it does have to fit into an economical envelope. But something like that suddenly can address, in frozen tension, a cantilever, for example. There's not much Fryoto cantilever. Most of the time you load on the edge. It can address all sorts of detail, from very formal ones to kind of edge detail, all sorts of conditions like that, because you do use the advantage of designing under tension, but you're not in tension anymore. You do not need a mast, you do not need a framework. The skin is freezing, basically, and is still double curvature, therefore it's a structure through geometry. Voilà. Thank you very much.
Thanks, Marc. Okay, does anyone have any questions for Marc? Yeah, down in the front here, Martin.
Hello. Dude. Look at it.
Hi there. Do your structures emanate a sound?
Sorry?
Do your structures emanate a sound with the wind blowing through?
No, not really. It does with the sound. When we deal with the transducer and we actually try to transform sound wave onto the piece itself, yes, there we directly get one. What we do notice with each of those pieces is a different acoustic. So most of them, you would just have a conversation with someone and you would walk in and directly you would stop and feel the sound get absorbed. The pieces themselves with the wind, it's not like it's a rattlesnake and the rivets are barely connected. Like I could do a PhD entirely on the type of rivet we are using. Actually, it's nothing like which is, you can find just online or something like that.
I was just thinking that some of them look like shells.
Yeah.
And in some communities, they use the shells to blow like a horn.
Yeah, no, we
I just thought it might emanate a sound if the wind was blowing through and causing convex.
Now, sound is one of those factors which, by the way, is often also a failing factor of shell structure. Most of the time, shell structure are so light, so thin, that they're actually the drama in terms of acoustic. Because anytime you kind of rain or something like that, it's just a tambourine or something like that. So sound is one of those criteria we observe right now, but we don't have the control yet. Yeah.
Where do you start? Do you start as a sketch? Do you start as a Rhino generative design? Do you start with a solid? Where do you start?
Yeah. It's a very good question. I think obviously there is not one single recipe, but what we've noticed is since we're very, very, in a way, very self-centered to some extent, we have a lot of research that one way or another did not aboutir on different projects. So you keep those in the back of your mind, and when you get the phone call of your client, you suddenly like, all right, where is it? It's far. Okay, that means I have to ship. I can't ship a large volume. Therefore, it needs to be flat, etc. And then you look into your research. Where did that work? Where did that not work? Oh, we like that, but that was not optimum, so we start bridging on that. But the most important thing where we do not start is anything which you can find online to some extent. And by that, I mean, it's never just a solid at start. It's never just a primitive. It's never primitive you stitch together. So all those mesh, because all are mesh objects, cannot, like I insist, they cannot exist flat, is because they are the result of many, many processes for that.
Ooh. Tal, because he's near me and I'm old.
I have maybe a technical question. So you're using a lot of stripes and the stripe fold, and I'm wondering if the actual fold on each stripe, is that a manual fold which is not structural, or do you make that with a press brake and give each one structural stability?
So all the type of projects should have different solution to that problem. So this one, for example, is folded, mechanically folded for that. So we actually give every fold is a mark, every mark gets folded, precise angle, and we have a way to offset on the digital side, but we also have a special dice that we do. Yes, that one stays, yes. The one like in Astana, for example, is an hybrid. On a similar stripe, it can partially take the curvature, and sometimes because it arrives to something which is much too tight or something like that, we mark the fold from that part.
Thanks for a wonderful presentation. I might have missed what metal you're using. I'm presuming that it's aluminium. Perhaps it's a trade secret which alloy of aluminium you're using. But my question was going to be, had you explored other material types? I mean, I'm thinking specific, well, the obvious thing would be composites. But I actually wanted to ask if you've ever tried it with ply, timber build-ups. And if not, what were the sort of reasons, technical or experiential, that sort of put you off the idea? I'm imagining that it's quite brittle at the points where you rivet. Could you elaborate?
So by order, yes, it's aluminium. Yeah, most of them are aluminium. Not a trade secret is into the 5000 series for the resistance to corrosion, of course. The age change based on if we need to mark the fold or not mark the fold. So we have sometimes softer, sometimes harder type of aluminium. We use different type of thickness. Yes, we've done composite. We're actually the first one having done the first carbon fiber shell ever applied to architecture in London, by the way, at Selfridges for an installation like 4 shells of carbon, which was also 1 millimeter of carbon at the time. So we do, unfortunately for us, most of our projects are in the US right now, and they are public work. It's extremely hard to win a competition proposing composite material because they will nail you down on the maintenance all the time. And even with aluminium, again, might be able to do a PhD on the rivet type, but we can certainly also have somebody at the office doing a PhD on the type of protection of paint. Some of those projects are actually cured 3 times just to protect the aluminium, because that's the type of questions that we don't not only get asked, but also that makes you win or makes you lose if you don't. So for that, then the wood is a little bit similar. We're fascinated by wood. We love wood. It is obviously a touch that none of the composite or the metal have in terms of aspect. But you know, any kind of ply, wood, even if it's marine, one way or another outside is extremely difficult to have outdoor. Without having a need of maintenance, and because those projects are public, you have to assume that there is zero maintenance happening. So that's also a kind of, and so early work, we did even work, even indoor installation work, we did something in wood, but as soon as we passed into the public, we got framed in a way or channeled into very strong maintenance questions and things like that.
A lot of your designs are static. Have you ever experimented with kinetic elements or?
It's an interesting question. It's something we have in the back of our mind, and we've been so focused to first demonstrate that it could work, that in a way we've lost it into our to-do list, you know. And it sounds, of course, it's a lecture, it's a conference. We make it sound easy, etc. But it's nerve-breaking every single piece. Every single piece, you go through so many challenges, and they go from anywhere. You know, the structure is one, but there is also the finishes is one. There is also the liability, which is another one. All sorts of things that are hidden behind that image that you forgot some of the premise you kind of would love to address. So up to now, we have not been into a kinetic type of thing.